Okay, now we're going to get a little deeper into electric potential differences. We'll define the electron volt. We'll write the total energy of an object. So the idea here is that you know how to solve problems using conservation of energy. Kinetic energy plus potential energy, gravitational potential energy, maybe some spring potential energy. We're going to add one more potential energy in there, the electric potential energy, EPE. So that now all of those things are conserved when you have electrical forces involved. Okay, an example, work potential energy and the electric potential. The work done by the electric force as a test charge, so there's the charge, that's the Q naught, moves from point A to point B, is this amount of work. So let's be clear about what that says. The work done in going from A to B is 5 times 10 to the minus 5 joules, measured in joules. It's a work, okay? Happy day. The test charge is 2 times 10 to the minus 6 coulombs. Happy day. And so we're interested in knowing two things. The change in the electric potential energy between these 2 points and the potential difference between these 2 points. Well, from concept 1, we know that the change in the electric potential energy is the negative of the work done in going from A to B. Well, we're given the work done, it's this number right here, and so that one just couldn't be easier. Just stick a minus sign in front of that work done and happy day. What about the potential difference between these 2 points? Well, that potential difference is defined as the change in the electric potential energy. Well, the electric potential is equal to the electric potential energy divided by the test charge. The change in the electric potential V is equal to the change in the electric potential energy divided by Q naught, just like we talked about in the last slide. And then this guy is equal to the negative of the work done. So we know what the charge is. Here's the negative of the work done, aka the change in the electric potential energy that we calculated in part A, and that gives us a voltage difference of 25 volts. You say, is that kind of like a car, maybe double a car battery? I say, yeah, that's what we're talking about here. And so remembering, though, what the delta means. Delta always means final minus initial. In this case, B is the final position, and A is the initial position. So delta V is the final minus the initial, and that's, we just calculated to be negative 25 volts. Well, that allows us to just solve this equation for VB. And how would we find VB? Well, we could just add VA to both sides of the equation. If we add it to the left, the VA will cancel out on the left, and then it'll appear on the right side. So here we've solved for VB, the voltage at point B. It's equal to the voltage at point A minus 25 volts. So what that says is that the electric potential, I mean, the proper way to say it is that the electric potential at point B is smaller than the electric potential at point A. You can also say that the potential difference or the voltage difference is equal to a negative 25 volts. How do we know that VB is smaller than VA? Well, if I take whatever VA is and I subtract 25 volts from it, then I'm going to get something smaller. Had I added, then VB would have been bigger. All right, so that's how to do that problem. 19-4, so we're moving right along with these concepts. State 2 rules of thumb for the electric potential. So here, we're going to start to develop some intuition about how these, how the potential works. The electric potential is high near positive charges and low near negative charges. How so? Well, the electric, like we talked about before with the basketball analogy, if that positive test charge is up near some positive charge, there's a big repulsion there and there's a lot of potential energy. It's like a coiled spring, like a compressed spring. There's a lot of potential energy there. In fact, that's a really good way of thinking about it, and I often think about it this way. Think about this positive charge here not wanting to be close to these positive charges here, and so that's kind of like a spring that you've coiled up, and there's a lot of potential energy associated with that compressed spring. So if there's a lot of potential energy, electric potential energy, associated with that situation, then because the electric potential is proportional to the electric potential energy, then there must also be a large amount of the electric potential must also be high. So the electric potential is high for positive charges, near positive charges, and low near negative charges. So we'd say that the electric potential is low here. Namely, if we put that test charge down close here, the reason is that they're really, really attractive. That positive charge wants to be next to the negative charge. And that the electric potential is high here, near the positive charge. Okay, and then number 2, the electric force pushes positive charges toward lower potentials and negative charges toward higher electric potentials. So let's see if we can analyze that. This force, the electric force, is going to push positive charges toward lower electric potentials. Well, that's just the same thing we've been saying, but in a little bit different way. We've got this positive charge here. If it's positive, as we've been considering so far, well, the electric force is going to be away. It's kind of obvious because like charges repel. And so it's going to push that positive charge away from positive charges. So this positive charge of the test particle, if we take a test particle, it's also positively charged. Okay, so the other part of the statement is that negative charges get pushed toward higher electric potentials. So now instead of having a test charge that's positive, let's have one that's negative. And if the charge is negative, and it's down here where the potential is low, it's going to get pushed away from these negative charges and toward the positive charge, toward the higher electric potential. So, 2 things to remember. The electric potential is higher near positive charges and high near positive charges, low near negative charges, and the electric force pushes those positive charges toward lower electric potentials and negative charges toward positive. Okay, I beat that one to death. C 19-5, write down the total energy of an object. Well, this starts to look pretty familiar to you. You say, well, hang on, that's just the kinetic energy. That's the translational kinetic energy. We talked about that in chapter 3 or 4 or 5, right along in there. This is 1/2 I omega squared. What is it called? The rotational kinetic energy. So if an object is rotating, has moment of inertia I, and then has angular speed omega, That's called the rotational kinetic energy. mgh, we know about that. That's the gravitational potential energy. The 1/2 kx squared, what's that called? Variously called the spring potential energy or the elastic potential energy. And then finally, the electric potential energy. So you can now solve problems with a lot of different things going on. A coiled spring, you can have gravity, you can have electric force, etc. So you can do a lot. Let's define the electron volt and derive its relationship with the joule. The electron volt, here's a definition. It's a little bit of a mouthful. It's the magnitude, meaning the absolute value, of the change in the electric potential energy of an electron. So this is EPE. Has the word energy on the end, so you know it means joules, of an electron. Well, you already know what the charge on an electron is. It's negative E. And what's E? E is 1.6 times 10 to the minus 19 coulombs. So it's the magnitude of the change of the electric potential energy of an electron in moving through an electric potential difference of 1 volt. Okay, so that's a mouthful. It's almost easier to see it with equations than it is with words. And here's how it works. 1 EV, EV is called the electron volt. And it is the magnitude, or the absolute value, here's the absolute value signs right here, of the change in the electric potential energy of an electron and moving through an electric potential difference of 1 volt. Okay, so let's figure it out. Well, if you'll recall that the change from the very first slide worth of concepts that we had, the change in the electric potential equaled the change in the electric potential energy divided by the test charge, right? So now we're actually just interested in this. So let me multiply both sides by the test charge, and we can see now that the change in the electric potential energy is just these two Q's cancel out, Q naughts is Q naught times delta V. All right, so that goes in here. And so we've just got Q naught delta V instead of the change in the electric potential energy. But now we're saying, what's an electron volt? Well, it's the change in the electric potential energy associated with an electron, and we know what the electron charge is, moving through a potential difference of 1 volt. Well, that's pretty cool, because here's the charge on the electron. It's minus E, which is minus 1.6 times 10 to the minus 19 coulombs, times the change in electric potential of 1 volt. So what do we get out of the deal here? We got absolute value signs here, so these guys kill the minus sign. This minus sign right here gets dead. And we've got 1.6 times 10 to the minus 19, that numerical factor, times coulombs times 1 times volts. Well, that's just times coulombs times volts. Oh, what's coulombs times volt? Well, you may remember that the volt, based on the definition in the previous concept, the volt is a joule per coulomb. And so if we just multiply both sides by the Coulomb, then 1 joule is a Coulomb times a volt. So this Coulomb times this volt becomes a joule. So let me just write this down again, just so we can get our heads around it. 1 electron volt equals 1.60 times 10 to the minus 19 joules. That's the bottom line of the relationship between an electron volt and a joule. Which one is bigger? Well, or which one's smaller? If you take a joule, which is something we've dealt with a lot, energy is measured in joules, or I mean, you have objects that have the gravitational potential energy of this would probably be something around a joule or thereabouts. You take a joule, whatever it is, and multiply it by, is this number big or small? You say, that's a small number, Dr. Edwards. It's a small number. It's 10 to the minus 19. So you're taking a normal size number, you're multiplying it by a really, really tiny number. And so you end up with an electron volt that it's very small. And you say, well, hang on, I mean, this is just 1.6 times 10 to the minus 19. That's the same as the charge on the electron. And I say, yeah, you're right. It is. So the conversion factor between electron volts and joules has the same numerical factor as the charge of the basic unit of charge, 1.6 times 10 to the minus 19. You say, well, why should we ever want a unit that's that small? And the answer is, it's used all the time in particle physics. If you want to know the energy of a particle, a tiny little electron or proton is never going to get energies associated with a joule or so. So it's used a lot in those. And we'll give you some problems to think about it with. All right, a little more detailed example. A particle has mass 1.8 times 10 to the minus 5 kilograms. And a charge 3 times 10 to the minus 5 kilograms, or coulombs. It is released from point A, that's here, and accelerates horizontally until it reaches point B, that's right here. And it's released from rest. So its initial velocity at point A is 0. The electric potential at A is 25 volts greater than the potential at B. So delta V final minus initial we're told that the electric potential at A is 25 volts greater than the potential at B. So this potential difference is going to be a negative 25 volts. Because the final potential, electric potential, is less than the initial potential, electric potential. All right, so what is the speed of the particle at point B? So this is a powerful, this shows the power of this, this formalism to be able to actually calculate that speed. We're going through a potential difference. This would be kind of like taking an electron and having it go between the two terminals on your battery. The potential difference there would be 25 or 12 volts, say. So let's see if we can work this out. We're going to use conservation of energy. We don't have any frictional or non-conservative forces to deal with here. And we can say that the kinetic energy at B plus the potential energy at B, the total energy at point B, equals the total energy at point A. That's this right here. And this is just a rearrangement of the equation. I have subtracted the electric potential energy at point B from both sides of the equation. So I subtract it from the left side, and it disappears, therefore, from the left side, and it reappears over on the right side with a negative sign. So then the relationship between the next step, I'm going to use the relationship between the electric potential energy and the electric potential, V. And how are those related? Well, the electric potential energy, well, the V is the electric potential energy divided by the charge. Remember, V is the electric potential energy divided by the charge. Well, that's the definition in the concept. Therefore, the electric potential energy is Q naught times V. So that's exactly what I've done in getting from here to here. The electric potential energy at A is Q naught times VA, and the electric potential energy at B is Q naught times VB. But there was a minus sign here, and that minus sign just comes along for the ride. Nothing more fancy than that. We can now take advantage of the fact that VA is 0. So this initial speed of the particle at point A is 0. And we now have a relationship between these two. 1/2 mVb squared equals Q naught times VA minus VB. Well, to solve that for VB, what we'll have to do, we're going to do some of these steps in our heads. You can work it out on paper if you want to. I want to solve this for VB. So what I'm going to do first is multiply both sides by 2. That'll cancel this 1/2. Divide both sides by m. That'll cancel this m and put an m in the denominator on this term. And that'll give me VB squared. Well, I don't need VB squared, I need VB. So I'm going to take the square root of both sides. And that gives us this equation here. So VB is the square root. There's the 2 that came over from the 1/2. Here's a 1 over the mass that came over from the mass that was on the left side. And then the rest of this 2Q naught VA minus VB just comes along for the ride. Now we can just plug in numbers. There's the 2. Here's the charge. Right here, 3 times 10 to the minus 5 coulombs. That's this number right here. Here is VA minus VB. You say, well, hang on, I thought that was a negative 25 volts. And the answer is not quite. VB minus VA is minus 25 volts. So if you multiply through this equation with the negative sign, then you get a minus VB plus VA equals plus 25 volts. So that says that VB minus VB plus VA equals 25 volts. Or the other more simple way to write that is V, just interchange the order of these two terms, and that'll be VA minus VB. And this is what gets placed in here. That's VA minus VB. Plug that in. And actually, we could have saved ourselves a couple of steps. We could have just said, well, I don't even need to really worry about delta V. We could just say VA minus VB. What's the information that we have about A and B? Well, it is that the electric potential at A is 25 volts greater than the electric potential at B. So VA minus VB had better be a positive number because VA is greater than VB. So we get the 25 volts, we divide through by the mass, 1.8 times 10 to the minus 5 kilograms, that's this number right here, and we get 9.1 meters per second. So that's what happens for part A. What's the speed of the particle? I mean, this is part A of the problem. Then we actually have part B to worry about as well. So what about part B? If the same particle had a negative charge and were released at point B. Okay? So now we're going to look at this from the other direction. Here's the scenario for part B of the problem. So we're going to talk about a negative charge here at point B. And let me actually see if I can get rid of some of that writing so we can actually see what we're doing. Eraser. All right. Miss some of this too. So I have some room to think about part B. All right, there we go. And now I can see if I can do this. Look at that. All right, so now we're free to think about part B. Here's my negative charge. It's starting at point B. And it's going to get pushed toward point A. So remember from the last concept that we talked about that positive charge, the electric force is going to push positive charges from higher potential to lower potential. So remember that the potential at point A is higher, so this is high electric potential, and this is low electric potential. In fact, we know what the difference between these is. It's 25 volts here compared to, say, 0 volts here. What matters, again, I mentioned this at the very beginning, what matters is the difference between the electric potential. So this could be 25 volts and this 0 volts, or this could be 50 volts and this 25 volts. What matters is the difference between the two. So now, this is still true that point A is at a high potential and that point B is at a low potential. But instead of having that positive charge being forced by the electric force from high potential to low, we've now got a negative charge, which tends to get attracted to the high potentials. So we're going to start him here and see how this, this works out. I'm going to start at point B, and that's my starting point, and my ending point is point A. So let's see what's going to change with the equations here. We're not going to have 1/2 mVA squared equaling 0. It'll be 1/2 mVB squared equaling 0. So in this case, VB is going to be 0, and we're going to be solving for VA. And what's going to change? This is not going to change here. We'll still have Q naught VA minus VB, and that will still be 25 volts. But we'll actually have 1/2 mVB squared, that's 0, instead of 1/2 mVA squared. So let's take this equation and see what it's going to look like now. 1/2 mVB squared now is going to be 0, and 1/2 mVA squared is not going to be 0. So there's the 0 for the 1/2 mVB squared, equals 1/2 mVA squared plus Q naught times VA minus VB. Okay, I'm running into these. That's supposed to say, oh brother, let me just write it down here. 0 equals 1/2 mVA squared plus Q naught times VA minus VB. Happy day. And we're trying to solve for VA. Well, to solve for VA, I've got to get this junk on the opposite side of the equation. So that'll come in with a minus sign. And so it'll look just like this. except there'd be a minus sign out in front here. You can do the algebra yourself if you don't believe me. There'd be a minus sign here, and there'd be a VA squared instead of a VB squared here. So then we do the algebra in the same way as before. The only change is we'll have VA here and then a minus sign here. So VA equals the square root of minus 2Q naught VA minus VB divided by M. That's for part B. All right, then plugging numbers in. Well, we're told that the charge is negative. So we're going to put, instead of a positive charge 3 times 10 to the minus 5th coulombs, we're going to put in a negative 3 times 10 to the minus 5th coulombs. That negative will go in here, and the negative sign from that negative number will kill that negative sign. And VA minus VB, that hasn't changed. That's still 25 volts. Mass still hasn't changed. The two negative signs cancel, and you get exactly the same result. So you get, again, 9.1 meters per second. Okay. Okay, that's how to do that problem. It's a little bit more involved than some of the other ones.